Okay, we're going to learn more about derivatives and their relationship with the gradients of tangents. We've seen before that the derivative is linked to ideas such as instantaneous rate of change from all of the previous learning we've done. Instantaneous rate of change, and from that, gradient of a tangent at a point. At a point on a curve. So let's develop that and see a few more examples on the rest of this video. First up, we've got a rule f of x, and we've got to find the gradient of the tangent line to this curve at point 1, -2. So the first thing we need to do is find the derivative of f of x, which is called f dash of x, as we know. And using the rule which we've already established previously, we have 3 times 3 multiplied by x to the 3 minus 1, which is 2, and then we have 2 by 6 subtracted off that times x to the power 1, and the derivative of a constant is 0, so that gives us 9x squared minus 12x for the derivative. Now at the point 1, -2, we have to use the x value in that point. So the coordinate 1, -2 has an x value of 1. So we're finding f dash of 1. So we substitute 1 into the derivative straight above there. So that's 9 by 1 squared minus 12 by 1. And that's 9 minus 12, which is -3. So the gradient of the tangent line at that point, without even having to draw it, without even having to sketch it, we know the gradient of the tangent at the point 1, -2 is a gradient of -3. Okay, we have a variation next up for our final example, which is split into 3 parts. And for each of the following curves, find the coordinates of the points on the curve at which the gradient of the tangent line has, at that point, this given value. So each of them have a given value for the gradient there. So first thing you do, we're given y. It's not in function notation form, that doesn't matter. So we have y equals x cubed. Now one of the possible notations you could use, you could call it y dash of x, because this is a function involving y of x, or you could just call it y dash as an abbreviated notation. Then the notations vary. There's lots of different types of notation which is covered elsewhere, and one of them is the simplified notation y dash. So it doesn't tell you quite as much as y dash of x. It doesn't tell you in regards to which variable, but it's accepted. So the derivative of x cubed is 3x squared. That's essentially the gradient function. So we know the gradient has a value of 8. So we can set that equal to 3x squared and then solve. So x squared is 8 over 3. And x will be the plus or minus the square root of 8 on 3. Which is plus or minus 2 root 2 over root 3. Now, optionally, you could rationalize the denominator, and which means we need to multiply the top and the bottom by root 3 over root 3. So this next step is kind of optional, but if you want the most elegant answer, you'll write it like that, because what I did was multiply the rationalize the denominator, which you might recall is multiplying the top and the bottom, in this case by root 3 over root 3. Okay, so if we multiply them, you'll see the answer there. So what we have now is an x or two x values. So the instructions actually say find the coordinates of the points on the curve, which is the original equation given in each case. So we just got to do some substitution in now. So coordinate off. So when x equals positive 2 root 6 on 3, we have to use the given equation. So we have to, it's y equals x cubed. Alright, so we have to cube this, and we have 2 root 6 over 3 cubed, which means we need to cube the top and the bottom. Okay, so that would be that there. Now that root 6 cubed is root 6 squared times root 6. So we've got root 6 squared is 6. So 6 eighths are 48 times square root of 6 over 27, and we can divide through by 3, and we've got 3 by 16 is 48. 16, so 16 is on the top, so root 6 is still there, and divide also the bottom by 3, and we get 16 root 6 over 9. So that's just when x equals 2 root 6 over 3. When x equals negative 2 root 6 over 3, y equals x cubed, so it's negative 2 root 6 over 3 cubed. Now that's going to be the same value as above, except for if you cube a negative, you get a negative. So to save time, instead of showing all those same steps above, it's really just the same answer with a negative there. So the points are, in the first case, 2 root 6 over 3, 16 root 6 over 9, that's your x and your y values. And in the second solution we have negative 2 root 6 over 3, negative 16 root 6 over 9. For the second example, y equals x squared minus 4x plus 2, and the gradient is 0. So I've quickly done the first step, find the derivative, and substitute the value for the gradient, which is the value for y dash, and solve, and we get x equals 2. So when x equals 2 in the original equation, same steps, but this one's a lot quicker. When x equals 2, y equals 2 squared minus 4 by 2 plus 2, which is negative 2. So we have the point 2, negative 2. Last one. Okay, finding the derivative, we have y dash is equal to negative 3x squared. Solving now, and we get two values, plus or minus root 2 when we solve, and y comes out as 4 minus square root of 2 cubed, or if you like, 4 minus 2 to the power 3 on 2, using your fractional indices. So therefore that point is, I might just leave it as a radical form. So it's root 2 and 4 minus root 2 cubed. You can use it, leave it in either form. And lastly, when x equals negative square root of 2, we do the same process. 4 minus negative root 2 cubed this comes out as 4 plus square root of 2 cubed, or 4 plus 2 to the 3 on 2 if you like. So that's it. That's our final point then, is negative of root 2 and 4 plus root 2 all cubed for the y value.